Good evening, everyone. Good evening, sir.
Hi, Mikey. How you doing? Good evening, the rest of you. Me want to when the rest of want to come on and don't say good evening. Mikey, do me a favor, please. What do I ask you to do for me? All right, never mind. Just check the chat for me, please, Mikey.
Okay, will do.
Okay. Good evening, everyone. How are we today? Okay, so clearly you're speaking and I'm not hearing you. So, all right. Are you hearing me a little better now?
Yes, sir.
Yes, sir. Better.
All right, nice. Let me confess something. I give up oxtail and rice and peas, gungo rice and peas, and sorrel drinks, and all of them something there for track and field. All right. So this is kind of night time of the year. So please to tell me that the television in the background is not disturbing you. Just say it's not disturbing me, sir, please.
It's not loud. It's not loud. Yeah, it's not disturbing.
All right, good. Because I am here cognizant that I have to teach, but also cognizant that things are happening around us, you know? All right. Only 9 of us here today. No, man, what is happening? 1, 2, 3, 4, 5, 6,
Because
7.
it's going to be a little bit late.
Okay, that's 10. All right, 11, 12. Okay. All right, so. All right, so we are continuing. I sat down today to do some writing of our exam questions. And then I recognize that, boy, I have a whole lot more reading to do. So I'm trusting that we'll be able to do a little more reading on our own. All right, so tonight I'm going to be looking at a section of the syllabus that speaks of the Earth as part of the solar system. Earth being part of the solar system. And I'm also going to be looking at the Nebula Theory. I'm also going to be looking at some simple accounts of the relative position of the planets. I will also attempt to look at the sizes as well as the materials that comprise the solar system. And I will also hopefully look at the sun and the planets and their interactions, talking about revolution, rotation, the retrograde motion, so forth and so on. So bear on. I should copy this and drop in the WhatsApp group. There's a video I want us to look at, but I don't want us to look at the video just yet. I want to have a conversation on this matter first, and then copy. And what is geology? Oh yeah, Paz did say that he's going to be a little late. Please. All right, so Ajabu, you know that you are my go-to person, don't? So you can just get your system ready, honey bunches, until teacher Shand is ready for.
Okay, sir.
Thanks, one. All right, so here goes. Let us have a conversation. Let us have a conversation. So, of course, you know the planets. The we know that we're talking about our solar system in particular here. You know, everybody knows what it is comprised of. How many of them they are comprised? It is the solar system is comprised of.
You're asking how many planets?
Yeah,
8 planets.
there are 8.
Yes, sir. Aren't there 8?
There are 8. Okay, you want to name the 8?
Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Is Pluto included? No, sir. 'Cause I know they said it's not considered a planet anymore.
Okay, all right. So we will go. All right. So they're talking about so humans have been searching for the answer for how the universe came to be. There has been nothing definitive, and the conversation still continues how the universe came to an existence. However, it has only been with a few centuries with the scientific revolution, that the predominance theory have been empirical in nature, right? Meaning that you're actually getting data from it. It was run about the 16th and to the 18th century that some astronomers and physicists began to formulate evidence-based explanation of how the sun, the planet, and the universe began. And we have been looking at different aspects of the whole universe in previous classes and the things that would have occurred and caused a lot of things to happen with the universe, right? Now we're moving to the solar system. So everything that we have done so far is working in tandem with now looking at the formation of the solar system. Now, when it comes to the formation of the solar system, the most widely accepted view is going to be called the Nebular Hypothesis. The Nebular Hypothesis. The Nebular Hypothesis, right? And the word nebula could mean something that is cloudy, something that is not so clear, something that is to be developed, right? You can look up the word nebula. Those are just my meaning of the word. But you can look up the word nebula to get some other meanings out of it, right? So pretty much in essence, the nebula theory states that the sun, the planet, and all other objects in the solar system were formed from nebulous material billions of years ago, all right? Originally proposed to explain the origin of the solar system. So this story has gone on to become a widely accepted view of how all star systems came about, right? So it is the theory that states that the sun, the planet, and all other objects within the solar system was formed from a nebulous material many, 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 many billions of years ago. All right? So according to that theory, the sun and the planets of our solar system began as a giant cloud of molecular gas and dust. A giant cloud, and you can understand now the word nebulous, right? So the word nebula comes from the word nebulous, right? And which is I was saying to you that it's cloud. So all of this is believed to begin from the clouds of molecular gas and dust. Then about 4.57 billion years ago, they say, something happened that caused the cloud to collapse, right? So we recognize now that the sun, we also recognize that the planets and all the other systems were formed or began out of this giant cloud of molecular gas and dust. Then about 4.57 billion years ago, something happened that caused this particular cloud to collapse. I'm giving you some very important points and some very important details that I want you to always remember. This could have been the result of a passing star. Some are saying that it could be a shock wave from a supernova. It could be the end result of a gravitational collapse at the center of that cloud, right? Talking about the gravitational collapse of the center of that cloud. Why is it that the cloud collapsed? There's nothing definitive that can say to you, this is a reason or reasons for the cloud to collapse. So there are many theories out there, and I would expect and suspect that we're going to be reading, watching more videos to see which view or views we could possibly use, all right? Now, from this collapse, pockets of dust and gas began to collect into denser regions. As the denser regions pull in more and more matter, conservation of momentum caused it to begin rotating. Think about it. Think about it. You have a balloon, or you have a sphere, and you're collecting material inside of that sphere. Now, as the material is being collected, you're going to have some levels of rotation taking place of that object. And of course, it's going to rotate, and it's going to stop rotating where these molecular particles will be at rest. So this is where you're going to be having the rotation. So the collapse of this cloud, right? Pockets of dust and gas began to collect into the denser region of it. The denser region dense means heavy. So think of you having a yoga ball. Everybody know what a yoga ball is? All right. Think of you having a football that is somewhat deflated. Somewhat deflated. Now, the denser portion of that ball is where the ball will be at rest. Where the ball lay down, that will be the denser portion. Now, what I'm saying to you is from this collapse of the cloud, pockets of dust and gas is going to be collected in this denser region. Means it will collect, and it is going to be gathered in that particular region. All right. And if by extension you want to extend your imagination, you have a tire, and water is collected in the tire, and mosquitoes are going to be breeding ground for the mosquitoes. It would be where the tire is upright. All right. Now, as the denser regions pull in more and more matter, it says that the conservation of the momentum cause it to begin rotating. So now, where you will have this cloud resting, you're going to be having this sort of gravitational rotation taking place. All right. Now, while increasing the pressure, it is going to generate some levels of heat. It's going to generate some levels of heat. So it says that most of the materials ended up in the ball at the center, while the rest of the matter flattened out into the disk that circled around it. So what is going to happen is that most of the material is going to come up to the center of this circle of this cloud. And the rest of the material is going to be, I would say, at the periphery, to the disk, circled around it, right? While the ball at the center formed the sun, and the rest of the material formed into some protoplanetary disk, all right? So this is how now you're going to be having the sun that is being formed, not S-O-N, but the S-U-N. And I said that because of the whole business of the creationist theory that we spoke about recently, all right? Now, it says planets formed from the accretion from this disk in which dust gas gravitated together to form even larger bodies is due to their high boiling points. Is due to the very high boiling points. So what is being theorized is that only metals and silicates could exist in solid form closer to the sun. And my question to you is, why is it that we're saying only metals and silicates could be closer to the sun? Let me see if you guys are thinking. Why only metals and silicates are closer to the sun? Question. Hello, somebody? Oh, I guess I am muted. If I say to you that only metals and silicates are closer to the sun, what things come to mind? What questions do you think you can ask yourself? And if you're thinking about it, only metals and silicates closer to the sun, why are only those things closer to the sun? Any ideas, any thoughts come to mind? Talk to me.
Sir, is it all right? Several thoughts came to mind just now. One of them is that the sun is a mixture of molten metals. So that's probably one of the reasons why you find them closer. As it disperse, they would change and maybe form new elements. So you find them closer at the origin, the source. And also I was thinking that just like the interior of the earth, where you have the metals, which should be in the core, it's a similar setup in the universe.
So let me ask you, what do you know the sun to be? The SUN.
A star.
Huh?
I know the sun is a star.
It's a star. Okay. What is one of the characteristics of the sun? The main characteristics of the sun. What do you think it is?
Very hot.
Very hot. Very good. And this is what I want you to do. I want you to be able to put on your thinking cap. So I like the conversation that we're going on with, but I also want you to put on your thinking cap. So, all right, hold on. Let me just respond to this lecture. PREFERE, preferably. BLY. All right. So yes, it is very hot. So my thing, due to their higher boiling points, only metals and silicates could exist in solid form closer to the sun. Right? Only metals and silicates could be closer to the sun because of their high boiling points. No, metals and silicates have very high boiling points. So you couldn't have those that are, well, the ones without that have low boiling points to exist because it's going to disintegrate. So you would expect that the ones closer to the sun would have higher boiling points. Talk truth.
Makes sense,
yes,
because it would have destroyed all of the organic elements.
Absolutely. That's the point. Absolutely. When I was a junior student of chemistry, sorry. Well, right. So what is happening? So what is happening is, I was going to give you an example. All right, let me go. Where was I going? One of my team members having an exam, and the students are not complying. So I was responding to him. I was going to go somewhere, but anyhow, it will come back. So, so if it is too hot, if the elements rather are going to be disintegrating, and I know where I was going. So when I was a junior student of chemistry, they're talking about the melting point of sodium chloride to be extremely high because of its structure. And the structure is one where it attracts a lot of heat. I mean, it's all foolishness. It's a foolishness. So me come home today and take one big spoon, you know, the big soup spoon. Yeah, man, me take one of them something there. Or if you want to call it ladle too, take one of them, put little table salt in it, and turn on my mother gas stove. No, me nearly done the 100-pound cylinder. I try and melt the salt. It couldn't melt. It couldn't melt. So I went back to school and I said to my chemistry teacher, you know, I tried melting the salt and it couldn't melt. She said, wait, now gonna melt. The amount of energy that requires to melt that, it's far more than what you think. And then when we look at the lattice structure now, you can recognize, when you look at the lattice structure of the silicates, those are so tightly bonded that it has a very high boiling point. All right. So due to the higher boiling points, only metals and silicates could exist in the solid form that is closest to the sun. And these would eventually form the terrestrial planets of Mercury, Venus, Earth, and Mars. All right. So I want you to remember those. Mercury, Venus, Earth, and Mars are those that, you know, have the higher boiling points closer to the sun. No, nobody never tell me that. Nobody have to tell me that, because the heat when me feel in a Kingston and recognize that me and JPS are enemies, and it don't make sense to turn on a fan because the fan is only circulating hot air, and it don't even make sense to go out a door because the mosquito then decide say go on back inside or else I can bite you up, and I'm just miserable. I remember one night, sometimes 3 times a day, just holding a shower because you're just hot and you're trying to cool down, right? Hold on a minute, please. All right. Now, let's just talk about Mercury. I'm just trying to bring something up to you guys so that at least you can use this to remember what it is that I'm talking about. For those of you who would have done sciences in high school, what is the main constituent of a thermometer?
Mercury.
Yes.
No
Yes.
alcohol.
No, the alcohol one, a foolishness, really. No, I mean, it has its purpose. The alcohol thermometer has its purpose, right? You're talking about something that is, you know, a little bit more sensitive. You can maybe use the alcohol. Yeah, it has its purpose. But the mercury one, no, man. Serious temperatures that can take. It can withstand serious temperatures. So it is supporting the point that I'm making. It is supporting the point that I'm making that that the high temperatures.
You're right, you know, sir.
Yes.
I have, all right, sir. I have 3 of those thermometers. I have the alcohol in glass that goes up to 100 degrees Celsius. I have a regular mercury that goes up to a little bit over 100, and I have another mercury that goes up to 500 degrees Celsius.
Yes, sir. Yes, sir. I'm if you tell you, sir.
Yeah,
Yes,
man.
sir. And guess what? You have some of the mercury one that goes, you have some that, you know, is red like minus something. You have the negative scale like -5, -10, -15 through 0 all the way up. Yeah, man.
That's true.
You know, play with them things, you know, to the point where when you're in the lab and you drop a mercury thermometer and the mercury is exposed, we have something that we put on the mercury because we don't want it to get into the water system, because mercury poisoning is deadly, and we can't just throw it into the garbage like that. So we have to put the powder on it, scoop it up, seal it into some glass container, and have those people who are in chemical disposal dispose of it. We have to have those persons dispose of it. It's very, very serious. We can't just go and say, okay, fine, we are going to somebody break a thermometer, we're going to try hide it and just, we can't do that. We can't do that, because if we do, we can actually poison ourselves, right? What's the point I'm making? Just to show you how high in temperature these are. So if you think of those, Mercury, Venus, Earth, and Mars, right? The temperature is going to be exceedingly high because of these silicates, right? And metals too. You will find them existing closer, very close to the sun. So if you're to put something on the solar system, you know exactly where those are going to go in relation to the sun. Very, very, very important for you to recognize. All right. Now it continues to say that because metallic compounds only comprise of a small fraction of the solar nebula, the terrestrial planets could not grow very large. Why do you think it couldn't grow large? Let me see if you're thinking. Why do you think it couldn't grow any large or larger than what it is?
Repeat the first part of the question.
I'm saying that the metallic elements only comprise a very small fraction of the solar nebula. The terrestrial planets could not grow very large. You know, we're talking about the terrestrial planet, you know, right? And we're looking at those that are metallic and have those high boiling points of the silicates, right? So we're saying that the terrestrial planet could not grow very large. And I'm asking, why you think it couldn't grow very large? Because what do you think about the heat being generated? Hello, somebody. All right. I get the feel that we are in class tonight, but we're not in class. I get the feel that we're in class tonight and we're not in class. And trust me, if anybody's supposed to have that feeling, it should be me, right? I want you guys to talk to me. What is happening? You have a coursework test today? You had a coursework test today?
No, sir, we didn't have one today.
You have a coursework that is due?
EIA for tomorrow.
You have a coursework that is due tomorrow?
Yeah.
Okay. So normally when I come to an online class and I'm getting this sort of feedback, it is suggestive that people are just logging on because they know the teacher is going to flip if you don't come to class. But the truth of the matter is you're here, but you're not here. You're here because you want to get your coursework out of the way. Which coursework is this, may I ask?
Environmental impact assessment.
Okay. All right. So let me know, what is the plan? Because I really don't want to come and just enjoy myself alone. I need to know, I need to have an agreement from you guys. What's the dealio? Hello, somebody?
I am good with class. I'm not sure.
Really and truly, Mikey, you're not the one that I need to hear from. If you ask me, your voice is the only voice so far that I'm hearing for the night. Where are the others?
Sure, I'm good with class tonight.
Thank you, Asia. All right. Do me a favor, Asia. I'm going to ask that you you play for me the video that I asked you to look at. And then now I'm going to be asking people what it is that they're getting from the video. Since I'm trying to explain this stuff first, so when we look at the video, we can follow. I'm going to ask you to just go ahead on and just play the video for me, please.
The universe. The solar system is old, like dial-up fax machine old. 4.6 billion years to be specific. The solar system has nothing on the universe. It's been around for 13.8 billion years, give or take a few hundred million. That means the universe is 3 times older than the solar system. Astronomers think the Milky Way is about 13.2 billion years old, almost as old as the universe itself. And it formed when smaller dwarf galaxies merged together to create the grand spiral we know today. Now it turns out the Milky Way has had about 8.6 billion years of unaccounted time, billions and billions of years to get up to all kinds of mischief before the solar system showed up to keep an eye on things. Our galaxy takes 220 million years to rotate, so it's done this about 60 times in total. And as it turns, it swirls and mixes material together like a giant space blender. Clouds of gas and dust come together into vast star-forming regions. Massive stars have gone supernova, and then the clusters themselves have been torn up again, churning the stars into the Milky Way. And this happens in the galaxy's spiral arms, where the areas of higher density lead to regions of star formation. So let's go back more than 4.6 billion years before there was an Earth, a sun, or even a solar system. Our entire region was gas and dust, probably within one of the spiral arms. So want to know what it looked like? Well, some of your favorite pictures from the Hubble Space Telescope should help. Here's the Orion, Eagle, and the Tarantula Nebula. These are star-forming regions. They're clouds of hydrogen left over from the Big Bang, with dust expended by aging stars and seeded with heavier elements formed by supernovae. After a few billion years, regions of higher density began forming into stars, both large and small. So let's take a look at a star-forming nebula again. See the dark knots? Those are newly forming stars surrounded by gas and dust in the stellar nebula. You're seeing many, many stars. Some are enormous monsters, others are more like our sun and smaller red dwarfs. Most will eventually have planets surrounding them, and maybe, eventually, life? So if this was the environment, where are all those other stars? Why do I feel so alone? Where are all our brothers and sisters? Where's all the other stuff that's in that picture? Where's all my stuff? Apparently, nature hates a messy room and a cozy stellar nest. The nebula that made the sun was either absorbed into the stars or blown away by the powerful stellar winds from the largest stars. Eventually, they cleared out the nebula like a fan blowing out a smoky room. At the earliest point, our solar nebula looked like the Eagle Nebula. After millions of years, it was more like the Pleiades star cluster with bright stars surrounded by hazy nebulosity. And it was the gravitational forces of the Milky Way which tore the members of our solar nursery into a structure like the Hyades cluster. Finally, gravitational interactions tore our cluster apart, so our sibling stars were lost forever in the churning arms of the Milky Way. We'll never know exactly what was here before the solar system. That evidence has long been blown away into space. But we can see other places in the Milky Way that give us a rough idea of what it might have looked like at various stages in its evolution. So what should we call our original star-forming nebula? Give our own nebula a name in the comments below. Thanks for watching. Never miss an episode by clicking
Understood what is happening? You want to go again?
Yes, sir.
Go again, sir.
Not so sure.
All right. Go again for me, please. Asia, thanks.
The solar system is old, like dial-up fax machine old. 4.6 billion years to be specific. The solar system has nothing on the universe. It's been around for 13.8 billion years, give or take a few hundred million. That means the universe is 3 times older than the solar system. Astronomers think the Milky Way is about 13.2 billion years old, almost as old as the universe itself. And it formed when smaller dwarf galaxies merged together to create the grand spiral we know today. Now it turns out the Milky Way has had about 8.6 billion years of unaccounted time, billions and billions of years to get up to all kinds of mischief before the solar system showed up to keep an eye on things. Our galaxy takes 220 million years to rotate, so it's done this about 60 times in total. And as it turns, it swirls and mixes material together like a giant space blender. Clouds of gas and dust come together into vast star-forming regions. Massive stars have gone supernova, and then the clusters themselves have been torn up again, churning the stars into the Milky Way. And this happens in the galaxy's spiral arms, where the areas of higher density lead to regions of star formation. So let's go back more than 4.6 billion years before there was an Earth, a sun, or even a solar system. Our entire region was gas and dust, probably within one of the spiral arms. So want to know what it looked like? Well, some of your favorite pictures from the Hubble Space Telescope should help. Here's the Orion, Eagle, and the Tarantula Nebula. These are star-forming regions. They're clouds of hydrogen left over from the Big Bang, with dust expended by aging stars, and seeded with heavier elements formed by supernovae. After a few billion years, regions of higher density began forming into stars, both large and small. So let's take a look at a star-forming nebula again. See the dark knots? Those are newly forming stars surrounded by gas and dust in the stellar nebula. You're seeing many, many stars. Some are enormous monsters, others are more like our sun and smaller red dwarfs. Most will eventually have planets surrounding them, and maybe, eventually, life? So if this was the environment, where are all those other stars? Why do I feel so alone? Where are all our brothers and sisters? Where's all the other stuff that's in that picture? Where's all my stuff? Apparently, nature hates a messy room and a cozy stellar nest. The nebula that made the sun was either absorbed into the stars or blown away by the powerful stellar winds from the largest stars. Eventually, they cleared out the nebula like a fan blowing out a smoky room. At the earliest point, our solar nebula looked like the Eagle Nebula. After millions of years, it was more like the Pleiades star cluster with bright stars surrounded by hazy nebulosity. And it was the gravitational forces of the Milky Way which tore the members of our solar nursery into a structure like the Hyades cluster. Finally, gravitational interactions tore our cluster apart, so our sibling stars were lost forever in the churning arms of the Milky Way. We'll never know exactly what was here before the solar system. That evidence has long been blown away into space. But we can see other places in the Milky Way that give us a rough idea of what it might have looked like at various stages in its evolution. So what should we call our original star-forming nebula? Give our own nebula a name in the comments below. Thanks for watching. Never miss an episode.
All right. So let me continue with what it is that I was attempting to explain. So I'm saying to you, those terrestrial planets, Mercury, Venus, Earth, and Mars, that are closer to the sun, is due to their higher boiling points consisting of metals and silicates. Thus, the existence of those planets closer to that part. Now, metallic elements only comprise of a very small fraction of the solar nebula. The terrestrial planets could not grow very large, right? As a result of the amount of heat that is generated or that is required because of their high boiling points, all right? Now, In contrast, the giant planets such as Jupiter, Saturn, Uranus, and Neptune were all formed
Yes.
right beyond the point of the origin of Mars and Jupiter, where the material is cool enough to volatile isocompounds to remain solid, frost-like, frost-line, right? These ice that are formed, that form these planets were more plentiful than the metals and silicates formed the terrestrial inner planets. So
That's the reason they are larger than the ones that are closer to the sun.
absolutely. So let's go back and look at what an atom looks like. The atom, the nucleus is in its center. And then you have these rings or orbitals that are rotating around. Now, the ones that are closest to the nucleus is smaller than the ones that are, the ring that is closest to the nucleus is smaller than the rings that are on the outside of the nucleus. So when we were doing chemistry, we were told that the first shell can hold a maximum of 2 electrons. The second shell can hold a maximum of 8 electrons. The third shell can hold a maximum of 8 electrons, and the fourth shell can hold a maximum of 8. But really and truly, as we go further and further, we recognize that the KLMN shell from the center all the way out can hold up to 18 electrons, right? So they get bigger and bigger and bigger as you move away from the nucleus, as you move away from the sun. Those planets will become will be larger in its nature. Am I making any sense right there?
Yes, sir.
Right. So the ices that form between these planets were more plentiful than the metals and silicates. Hold on, please. Hold on. All right. So, oopsie daisy. Hold on, guys. All right. So, what I want you to recognize that the ice that is formed by these planets were more plentiful. Of course, you can think of the size also than the metals and silicates formed from the terrestrial inner planets. This allows them to grow massive enough to capture large atmospheres of hydrogen and helium. These are leftover debris that never became planets that were congregated within the regions of the asteroid belts. I remember the guy in the video talking about this leftover from the Big Bang Theory. You remember him saying that?
Yes, sir.
Right.
And then it was blown away.
It was blown away eventually, right? So which is why Jupiter, Saturn, Uranus, and Neptune were so massive enough, right? As a result of that. Now, some 50 million years ago, the pressure and density of hydrogen in the center of all of what it is that we're discussing here was great enough to begin some sort of thermonuclear fusion, right? The temperature, the reaction rate, the pressure, and the density also increased until they achieved some level of equilibrium. At this particular point, the sun became the main sequence star. The solar wind, the sun from the heliosphere swept away, the remaining gas and dust from the stuff from the Big Bang Theory we spoke about, ending into some sort of planetary formation process. All right. So if you look at it, you'll recognize that all that we have looked at so far, one is connecting the dot to the other, which is connecting the dot. So it's a puzzle that we're looking at. And even though we're talking about the nebulous theory, there are differences to it, and I soon get there, because there are others who are thinking otherwise and come up with something else from this nebulous theory. Matter of fact, let me look at the some different ideas. So the idea that the solar system originated from the nebula was first proposed in 1734, right, by a Swedish scientist, Emanuel Swedenborg, right? Now, he developed a theory further and published it, to talk about the gaseous clouds, the nebulae, the slow rotation, gradual collapsing, and the flattening due to gravity, and the forming of stars and planets, which is what I discussed with you earlier. A similar but smaller, more detailed model was proposed by Pierre Simon Laplace, right? And Laplace theorized that the sun originally had an extended hot atmosphere throughout the solar system, and that protostar cloud cooled and contracted. Now, as this cloud spun more rapidly, it threw off material that eventually condensed to form the planets. So that is Laplace theory, all right? So what he's saying again is that the sun that was originally had an extended hot atmosphere throughout the solar system, and that this protostar cloud cooled and contracted. Now, the cooling of this protostar and the contraction of it caused the cloud to spin more rapidly, and it threw off materials that eventually condensed to form the planets, right? So that was his theory. Now, what they call the Laplacian nebula model now was widely accepted during the 19th century. So what they did was to merge both of them together, to come up with something that was more acceptable in the 19th century, but it had some rather pronounced difficulties. The main issue was angular momentum distribution between the sun and the planets, right? Was an angular, momentum distribution between the sun and the planets, which the nebula model could not explain, all right? So which is why they adopted the Laplace theory, right? And, say that, boy, this thing here makes a little bit more sense. So they now call the Laplacian nebula model, right? No, hear what happened. The main issue, as I said before, is that the angular momentum distribution between the sun and the planet, the nebula model could not explain that. So there came now a Scottish scientist, James Clerk Maxwell, who asserted that different rotational velocities between the inner and outer parts of a ring could not allow for condensation of materials, right? So the man come disturb different processes, right? But something that they could think about. All right, so I'm going to read something here for you. I'm going to read something here for you. So it says, Sir David Brewster, in 1781 to 1886, birth and death, stated that those who believe that in the Nebula Theory consider it as certain that our Earth derived its solid matter and its atmosphere from a ring thrown from the solar atmosphere, which afterwards contracted into a solid terrestrial sphere from which the moon was thrown off by the same process. Under such a view, the moon must necessarily have carried off water and air from the watery and aerial parts of the earth and must have an atmosphere. I'm going to drop that into the WhatsApp group, and I'm going to ask that you look at it. I'm going to ask that you read it over. I'm going to give you about, let's see, how can I'm going to drop this in a WhatsApp group. I'm going to ask you to read it over so we can have a closer look at what is happening here. All right? I'm going to give you about 5 minutes to read it, and you tell me what it is that you're getting from it. All right, there goes. All right, let me just try it here.
Excuse me, sir.
Yeah, man, go through now, what on.
Oh, can you please repeat who introduced the Nebular Theory and when was it introduced?
Sorry, say it again.
Who introduced the theory and when it was introduced? When and who introduced the theory?
Of the Nebular Theory?
Yes, sir.
All right, no problem. Matter of fact, I should ask you to go and research that, because I mean, I can tell you, but I want you to tell me who proposed it. But I have the information here. All right, I'm coming. Sorry, I want you to read this for me in the meantime, and we're going to have a conversation about this. All right. Now, if I were to go back to what Sir Kant and Sir Laplace spoke about. Sir Simon, you know, kind of had a challenge, right? And he's saying here that those who believe in the Nebula Theory consider it as certain that our Earth derived its solid matter and its atmosphere from a ring thrown from the solar atmosphere, which afterwards contracted into a solid terra-aqueous state from which the moon was thrown off by the same process. Under such a view, the moon must necessarily have carried off water and air from the watery and aerial parts of the Earth and must have an atmosphere. Now, let me just say something. It's by the 20th century, the Laplacian model, and the Laplacian model, it had fallen out. The Laplacian model, remember, is a combination between Laplace and Sir Kant, who came up with the Nebula Theory. So it's a combination of two, right? By the early 20th century, others were not believing in that model anymore, promoting scientists to seek out new theories, all right? However, it was not until 1970s, you see, 1970s, you know, some of your parents were born in that era, 1970s, that the modern and most widely accepted variant of the Nebular Hypothesis, the solar nebula disk model, the solar nebula disk model emerged. Let me just say something to you. It's all about it is that we're studying about the Earth. It is evolving. It has not yet evolved. It is present continuous. It's not a past tense. Because the 1970s was just around the corner. Just around the corner. 70, some 50 plus years ago. Just around the corner. All right? And they fell out of love with the Laplacian model and was able now to say, here the plan. We have a variant of the Nebula Hypothesis, and we're going to call this variant the solar nebula disk model. Now, credit goes out to some astronomers, you know, and you know others who would have done some work, right? And in this particular model, it has been successfully explained that the appearance of the accretion disk around the young stellar objects, the variations demonstrated that the accretion of materials in these disks led to the formation of few Earth-sized bodies. Thus, the region of the terrestrial planets that we spoke about earlier is now considered to be an almost solved problem. Anybody remember what the terrestrial planets are?
Mercury, Venus, Earth, and Mars.
Thank you very much. All right. So those terrestrial planets, very good. Thanks for listening. Those terrestrial planets are now considered to be an almost solved problem, right? While originally applied only to the solar system, the solar nebula disk model was subsequently thought by theorists to be at work throughout the universe. And they use it to explain many formations of many exoplanets that have been discovered throughout our galaxies, right? But guess what? Notwithstanding, there is a problem. And you know, because we're such bright people, we're going to find some issues with it. What they're saying is that although the Nebula Theory is widely accepted, there are still some problems with it that astronomers have not been able to resolve. For example, there is a problem of tilted axes. And when you look at your syllabus, it asks us to talk about sizes. It asks us to talk about the materials, terrestrial planets, gas giants, ice giants. So we'll talk about the materials, the terrestrial planets, you know. You know what those four are. You talk about the gas giants, you know what they are. Ice giants, those are the terrestrial stuff. Talk about the sun and their interactions, the revolution, rotation, the retrograde motion, the relative position of the planets, right? So all of that is what it is that we're looking at under the Earth as part of the solar system. So this is the issue. The main problem they are saying is that astronomers have been able to resolve is that there is a system or an issue with the tilted axes. So they say, according to the Nebula Theory, all planets around the star should be tilted the same way relative to the ecliptic model there. But we have learned that the inner planets and the outer planets have really radically different axial tilts, right? So that is the issue that, trust me, I'm expecting anytime now or sometime later for some new discoveries to come about. So even when we would have fully finished doing our studies, there are going to be additional studies coming around to explain what is happening there. It says, whereas the inner planets range from almost 0-degree tilt, others like Earth and Mars are tilting significantly, some 23.4 degrees and 25 respectively. All right. Outer planets have tilts that range from Jupiter's minor tilt of 3.13 to Saturn and Neptune more pronounced at 26.73 and 28.32, right? To Uranus's extreme tilt of 97.77, which is, they're saying its poles are consistently facing towards the sun. All right. So those are some issues that I really want us to continue reading so we can have greater understanding as to what is happening right here. It says also that the study of the extra solar planets have allowed scientists to notice irregularities that cast doubt on the Nebular Hypothesis, right? They are theorizing that some of these irregularities have to do with the existence of the hot Jupiters, right? That are close to their stars and periods of just a few days. Astronomers have adjusted the Nebula Hypothesis to account for some of these problems, but you know, the truth is they are yet to address all outlying questions. It is evolving. That's all I can say to you. The conversation is continuing. It's for us to have an idea what is happening, and then to follow suit what is to come. And you know, let me just stop right here and just make a plug how important it is for us to read. And it is in reading that we are going to be able to see the answers to these questions. You know, we'll watch the news, you know, listen to the developments so we can know when additional discoveries come about, you know, because you have these scientists, these astronomers, these cosmologists, these physicists and chemists, the biologists also, they continue to work so that these missing dots can be found and the gaps can be filled so that we can have a fulsome understanding of the origination of what it is that we are here experiencing and living up. All right. So it seems that it questions that some have to do with the origin that are, you know, the toughest to answer. You know, the truth is when we think that we have some satisfactory explanation, then there comes some issues that we really can't answer. That's just the honest truth. I can't tell you what they are. And there are others who are even more pronounced, can't tell you what they are. What the literature is, however, suggesting that between the current models of the star and planet formation and the birth of our universe, they have come a very long way, right? they're saying that they are learning more about the neighboring star system, and they are exploring more of the cosmos. Their models are likely to mature further, which is what I'm saying. It is developing, a developing concept, something that we ourselves are trying to grasp, to understand. Geology depends so much on the physics, and it depends so much on the biology. It depends also on the geographers. It depends on all aspects, the mathematicians, you name it. So it is that these unanswered questions can really be answered, or we get closer to what is happening, right? But importantly, that I want you to leave with class tonight is that the higher boiling points of these metals and silicates could exist in solid form closer to the sun, and these would eventually form the terrestrial planets of our Mercury, Venus, Earth, and Mars. So we know what our terrestrial planets are. So if there goes a question to write about our terrestrial planets, you know what the terrestrial planets are, and why they are called terrestrial planets, because of these metallic elements are comprised in them, the metals and the silicates, and only we are comprised only to a very small fraction of the solar nebula, and it is believed that these terrestrial planets could not grow very large. And then also we look at those in contrast, to those terrestrial planets that are referred to as giant planets. And of course, these would be Jupiter, Saturn, Uranus, and Neptune, right? And of course, the formation is as a result of these ice that form the planets that were more plentiful than the metals and silicates. And this allows them to grow very huge, massive, to capture atmospheres of hydrogen and helium. And trust me, if you want to, who was I saying this to? Oh, on Saturday when I was having my Foundation 3 class, I was saying I was linking, every concept that I taught, I was linking it to the real world, and the students were saying, "Sir, me never this much them ways there." And I'm saying to you, when the geology is linked to the real world, we can have a better understanding as to what is happening. I remember years ago, about 1980, it's either 1982, no, hold on, I won't tell you. It could be December 1981, if I'm not mistaken. December 1981, I believe it was. And from my memory, I'd have to call my mom and ask her. I remember, my mom was getting me ready to go up along Constant Spring Road by the plaza, because this was Christmas, and back then in Christmas we had these heavy helium tanks, in the Harford region, blowing up balloons. So I don't know the affinity of children and balloons, but I had to get my balloon, and I think we went there like days before, got some balloons, and of course I was reckless with my balloon, and I bawled living eye water because I watched my balloon fly away into the the abyss. It just went, and I was promised that we're going to go back to have the stuff done up. No, the family home was close by. And while we're there, I mean, we were on our way there. We heard a huge explosion. When I say huge, I mean to the point where, in my view, I could call it as a creator, something that just shattered the glass out of many of these businesses. Literally, people's limbs were blown off. May I talk about in a Jamaica, right? So if you don't believe me, you can go talk to mommy and daddy or grandpa or grandma. And to this day, there is a gentleman who rides up and down in a wheelchair who is believed to have been in that blast these many years ago, some almost 40 plus 41, 42 years ago. Now, why am I saying this to you? Because you see, when it talks about it says that the ice that are formed in these planets were more plentiful than the metals and the silicates in these terrestrial planets. We're talking about the giant planets now, right? Allowing them to grow massive enough to capture large atmospheres of hydrogen and helium. And it is believed to be these leftover debris from the Big Bang. Now, when I remember, and this is not something that I've read, this is something that I witnessed. There was a lot of bloodshed in the area. We went back home, but of course the news came, and of course back then we never had no telephone. We had land phone, but the land phone was, it's not everybody had a land phone, and the land phone is one where you had to put your finger in something and turn it around. We don't know if anyone only know what we're talking about, right? Then phone where you want dial 9, you have to put the finger in at the 9 and wheel something come round and wheel it come on. So those are the telephones we had. And then big and heavy. The telephones back then were big and heavy. So
yeah, man, sir, we know them, man.
You know them?
Yeah, man.
Rockstone. So what used to happen is that I remember we had a telephone, but our immediate neighbors didn't have a telephone. So it's not that we could call them like, no, we can just, take out the phone and do anything quick. We never had them something there. So we had to be running to the neighbor's house. And, recently I drove through the area because, of course, we moved out of the area. I drove through the area and I looked at it and I tears almost came to my eye because I'm saying to myself, this was liberty. You could go to your bed with your doors open and nobody now come inside of your house. The man them see a mango tree and want a mango, them and knock on the gate and ask if them can get the mango. Me now make up no story. So when nighttime come, we used to be on the road playing and, oh my God, Lord, trust me. So let me just stick with it. So the helium and the hydrogen balloons are something that grow big. And them light. They're light in nature. So that's why they were able to fly up and down in the air. So when you get a helium-filled balloon, it stand up in the air. You ever cut the string and see how far it gone? It gone left you. So this thing makes a lot of sense to me that these giant planets, right? That were more plentiful than the metal and silicates that form the terrestrial inner planets. And they were allowed to grow massive to capture these helium and hydrogen gases. Think of those helium gases, filled balloons, how big they are blown up, and how light they are, and how easily they can navigate through atmospheric pressure and go about because of this lightness. All right? So, and all of this was, as I said before, is believed to be leftover hydrogen and helium from the Big Bang theory. Now, sometime later they may come and say it was, it could be generated as a we call it no, as a bygas, or a byproduct of the high temperatures of these bond making and bond breaking. Because remember, when we had that sort of catastrophic event, a lot of things were being created and things were moving around, and you had those small particles coming together to form newer particles. And this is how we spoke about the galaxies and the stars were created. Now, the fusion of those galaxies and stars was able to be achieved because of the whole business of bond making and bond breaking. And the result of these bond making and bond breaking could be as a result of these products that will come off. And one of the products could be oxygen. It could be hydrogen as one of those byproducts, right? So it could also explain, and this is me thinking outside of the box based on the chemistry that is taking place up there. That could be as a result of the added hydrogen that exists, within the solar system. So it is an area that is developing, as I said before. What I tried to do tonight is to again whet your appetites. Remember, an area like this, Mr. Walder, Mr. Shand, or whomever is presenting the course cannot definitively say this is this. We may have an idea to say, yes, this sounds plausible. But remember, we are not doing any research to come and say, okay, this is it. We have to depend on those who are conducting these research. And the research is going to prove otherwise to say, here the plan. Laplacian model? Nah, we're going to replace it with this, etc., etc. So we have a series of models, coming out from Kant with the Nebula Theory that Sir Laplace came up with later. And then, of course, you have others, Emanuel Swedenborg, who talking about some other things. And then you're going to have Pierre Simon, who is saying that this is this. And then you're going to have people coming out like Sir David Brewster, who is going to reject what these guys are saying, right? But the truth of the matter is, we know that these planets exist. And we know the ones that are terrestrial versus the ones that are giant. And we can explain why it is that these terrestrial ones are smaller compared to the giant ones. And we can hypothesize why the giant ones are giant, and, etc., etc. I will stop here. Are there any questions?
Sir, I sent something in the chat.
G's and P's, say from your top, me not looking at the chat. All right, good, there's only two things. All right. What is this from HRM? I don't understand that, Denicia. What is that?
Oh, sir, you were asking if you have any upcoming assignments.
Oh, got you. So allow me to look on the chat from 8:30. Yeah. No, man. Soderbergh, no. Which of the theory we're asking about first? The Nebula Theory first, Denicia?
Yes, sir.
No, man, that's Kant. You follow what I'm saying?
Soderbergh made which theory then?
I'm not hearing it, honey. Talk to me, please.
Excuse me, sir, can you repeat?
No, I'm saying, talk to me. You're saying something about what?
Oh, I was saying, so Swedenborg made which theory, proposed which theory?
Right. So Swedenborg also proposed a theory. The whole Nebula Theory also, right? in okay, so he Swedenborg, Emanuel Swedenborg proposed the nebula theory back then in the 1700s, right? And then Immanuel Kant was very familiar with his work and developed the theory further.
Okay, so Swedenborg proposed the theory, but
He proposed the theory, right? He developed the theory, yeah, right. It's like, let me see, no, something that I can recall, no. Like Pythagoras' theorem, is Pythagoras? Yeah, I'm not him come up with this first. Somebody talk something and him catch it and him run with it and go develop it and come out and call it Fremon. You know them things there. That's why when you have the ideas, you see, go and go patent it first and then you talk to your friends after. So if your friends come out with it, at least the patent say is you first come out with it. So Immanuel Swedenborg first proposed something, but Kant they say, me familiar with what Swedenborg did, and then I'm going to develop this theory into something more. So he first proposed it, then Kant developed it, then Laplace went on and said, boy, me not to believe everything what you say, but me believe what you say, and I'm going to develop a little bit more on what you did. So the Nebula Theory now was replaced as the Laplacian theory, right? So in believe, and they call it the Laplacian modular theory, or the model, nebula model, right? So he added his stuff, and this is Pierre Laplace. He did some stuff to it, and then now Sir David Brewster come out and say, "You're the plan." Me have a different idea, right? So yes, I don't know if that answers your question, dearest. Does it? Denicio?
Yes, sir, I understand now. Thank you.
Yeah, no problem. All right, guys. You have 5 minutes to go and do some more work now on the stuff, but here's the plan. When I come to my class, come sit down and do no teacher work in my class here, because me don't want to do my work in a teacher class. I want you to come to class so that we can have a conversation. What I'm doing, and hear me out, and I keep saying the same thing, I'm going to take 2 minutes to say this to you. It's when we were studying, and I said we because we studied before the advent of Google and them something there. When we were studying, all we had were encyclopedias and textbooks that we could go and read. We never have no video where somebody can extract and show a picture and animate, so forth and so on. We had to go and read textbooks to get this stuff. What I'm doing with you, and we never have nobody to explain what we're reading, so we have to read and understand and go and write paper out of our head. So see all these names that Dennis is asking about, Swedenborg and Kant and Pierre Laplace and Brewster and them. So we had to remember those names and the year, the 17. Sometimes I couldn't even remember, like 1734 and 1755, right? So we said that the early 1700s, man can't mark it wrong, come right? And then by the mid 1700s, 1755, and mid 1700s. So, these are things that we had to speak about. No, you guys have all this information at the tip of your fingers. So what my purpose now is to come to class, talk to you about it, give you the sort of explanation that we can give, have some conversation, send you out now to go read on your own and to watch videos to concretize what it is that I would have done. Very, very important. And I'm going to say to you how important it is. You have to understand all of these granular stuff that I'm doing, because I can ask you a question about the giant planets versus the terrestrial ones, and you need to know which is which. In your own words, describe. All right? So you have to go understand it to describe in your own words. We don't want nothing from the internet. Anyhow, bless your hearts. We'll talk. Take care.
Okay, sir.
Cool.
Okay, bye, sir.
Bye-bye.